Now we discuss Dijkstra's algorithm. We start with a graph G and a weight function on the edges. Given any path P, we define its weight of the path to be the sum of the weights on the edges. So in some real-world applications, the weight on an edge might be the distance of that part of the road, or the amount of gas a car will use to go down that road, or the amount of time it takes to travel. As you can see, there are many different parameters, so we tend to just keep W as an arbitrary function, which is important because, for instance, when you're trying to use a computer to get driving directions, it often optimizes based on different options, and what it's optimizing is actually using different weight functions. So anyhow, we've got a point A and a point B, a V and a W, and we want to find the shortest path from V to W. In other words, we want to find the VW path where the weight is the smallest it can be. So Dijkstra's algorithm actually does more than that. It finds the shortest paths for any target vertex starting from some V. So here's how the algorithm is going to work. We're going to assume that we have some starting vertex, a graph, and a weight function. Then for every other vertex in the graph, we're going to define its weight temporarily to be 0 at U and infinity everywhere else. This weight function is going to represent the weight of the shortest path to the vertex eventually. So right now it's the weight of the shortest path found so far, and if it's infinity, it means we haven't found a path yet. Likewise, we're going to define h of v to be u for all of v. That's just to get the algorithm going. As the algorithm goes on, we're going to update the weights whenever we manage to find a path from u to v. And then when we do so, h of v is going to represent the last vertex on the path before u, so that then you can trace it back, as we'll see. So we're going to use a while loop. First, we consider all the vertices in our graph. As long as there's a vertex left we haven't explored, we're going to choose the vertex in our set of smallest weight. Note that on the first run of this algorithm, that vertex of smallest weight is going to be u itself, because it's the only vertex of weight that's not infinity. Then for each edge adjacent to our vertex x, we're going to do this comparison. Namely, if the weight of x plus the weight of the edge xy is less than the weight of y, we're going to change the weight of y to be the sum on the left, and we're going to set h of y equal to x. In other words, what we're doing is we're taking some vertex x that we already have found a minimum path to, and for every edge incident to it, we're looking at y, and what this summation on the left is saying is the weight of this path smaller than the weight of the current shortest path we have from u to y? If so, then we're going to change paths. So now we know that the shortest path from u to y goes through x before it hits y, and so that's why we're updating h. And the new weight of y, the shortest path to y, is the red plus the blue, which is this expression. And then finally, we remove x from the set of vertices to consider. And so what happens is if at some point you get a vertex with weight infinity, what this is going to do is it's going to say, okay, you have found a vertex we haven't found a path to yet. We're going to start by making that path our shortest found so far and update the numbers accordingly. And then later, if it pops up again in this algorithm, then that means we found a shorter path and we're going to replace our path. And what I mean when I talk about replacing the path, the point is once the algorithm is finished, given any vertex v, we know that if you follow backwards, if you keep applying this h function enough times, you'll eventually get back to u. And so the point is the shortest path is going to be this one. It ends at v, the vertex right before v on the path is h of v, the vertex right before that is h squared of v, and so on until you get to u. And you don't have to actually add up the weights because the way the algorithm works, you've already computed it. The weight of this path ends up being w of v. So let's work with an example. This is going to be my example graph. There's my initial vertex u, and these are my edge weights. And so the point is we're going to find the minimum weight path between A and every other vertex in the graph. So for the next thing, I've initialized my W function. It is 0 at my starting vertex and infinity everywhere else. And W consists of capital W consists of all of our vertices. Currently, the one of smallest weight is our initial vertex, so we start with that. And we're going to look at every edge from the initial vertex. So first we have this edge. We see that 0 plus 1 is less than infinity, so we have to apply our algorithm. And so by our algorithm, we now update the weight of b to be that sum, so it's 1. And h of b is a. So we see that we have found the shortest path between a and b so far is this edge of length 1. Is what that's saying. And we get to b from a by going through a. Okay, now let's consider this edge. Again, the same thing happens. We see that 0 plus 2 is less than infinity, so I replace my weight on c with 0 plus 2, also known as 2. And because I've changed it, I need to update the value of h to being a. And now I've finished, and I remove a from the set of vertices I can consider. And so now I look at the remaining vertices. Most of them have weight infinity, but there's a vertex of weight 1 and a vertex of weight 2. So according to my algorithm, I start with vertex b of weight 1 now. And I'm going to look at each of its edges and then see if I need to update things. So again, we're looking at each of its edges one at a time. And we see this vertex. We have the feature that 1 plus 2 is less than infinity, so we replace that number with 3. And then we also update the other function to say that our shortest path from A to H goes through B. Then the edge 1 plus 4 is 5 is less than infinity, so we also update that and replace it with 5. And 1 plus 6 is less than infinity, so we replace that number with 7. In each of these cases, we include b to tell us that the shortest path from A to these vertices discovered so far has to go through b. Okay, now we have 4 different vertices that have a finite weight, but 2 is the smallest of these numbers, so our next step is to go through vertex A, and there are 2 edges. And as a rule, it turns out we never worry that much about the edge going back to a vertex we've previously discovered, because if that edge happened to be on the shortest path from u to our vertex already, then going back the way we came is only going to increase the number rather than shorten it. There's other reasons later we'll discuss, but we'll discuss them when they hit those types of paths. So this is the only edge that actually matters right now. And we see that 2 plus 3 is 5. It's the same size as what it currently is, so we don't need to update anything. So now we've already gone through these 3 vertices. The remaining vertices have weight 3, 5, and 7. 3 is the smallest of these, so that's the vertex we're going to consider next. And these are our 2 edges incident to H. One of them goes to the current path from A to H. So we know we can ignore that edge, so we only need to pay attention to this one. We see 3 plus 1 is 4, that's less than 5. So now we see we actually need to change one of our labels for a vertex that we've already changed the label for before. The point is, so far the shortest path we had found goes A to C to D, but now we've discovered the shorter path by weight goes from A to B to H to D. And so we update accordingly. Now the weight of H is 4, or weight of D is 4, and then we've switched the B with an H to tell us that the path from A to D has to go through H. So now that we see we've got vertices of weight 4 and 7, 4 is smaller, so vertex D is the one we consider next. It has 4 different edges coming off of it. And we see in 3 of these examples, 4 plus that weight is smaller than the weight we have at those vertices, so we're not going to change anything. So this is the only edge that really matters. So we have 4 plus 1 is 5, and 5 is less than 7. So it looks like we're going to need to replace this weight with 5 and replace the B with D. So let's do that. Now we're in a position where we've only got one vertex left with a finite weight, so we consider it. It has 4 edges coming out of it. 5 plus 6 is bigger than 1. 5 plus 1 is bigger than 4. And so we don't update these vertices. But 5 plus 1 is less than infinity. And 5 plus 3 is less than infinity. So these last 2 vertices we're going to update by making their weights 6 and 8. And the labels E and E. And so it's worth pointing out, this means the shortest path we've found to F so far comes from E, which comes from D, which comes from H, which comes from B, which comes from A. So it's this path right here. So now we've got only 2 vertices left to consider. Let's consider the one with the smallest weight. That's vertex F. We've got 2 edges coming out of it. 6 plus 1 is bigger than 7. 6 plus 1 is less than 8. So we see we need to adjust this last vertex and make it have weight 7. And the shortest path to G from A must be going through F. Now finally we consider the vertex F, but here we see there are no more updates, and now we've finished exploring every vertex in the graph. And so the point is, given any of these vertices, the weight tells you the weight of the shortest path to that vertex starting from A, and the other entry tells you which vertex you need to go to along that shortest path. So for example, let's take the path from A to G. So we see it's going to have weight 7. We see the path must have F as its penultimate vertex. And we see this labels E, so we have to have gotten to F from E, from D, from H, from B, and finally from A. So this ends up being our path. And you can see the weights along the way is 1, 2, 1, 1, 1, 1, and that does add up to 7. And so this is the path, and the point is all other paths you could take in this graph from A to G is going to end up involving a higher weight or the same weight.